Hi everyone. In this video, we will investigate the effect of pressure ratio on the performance of the Brayton cycle. The question is, what would happen to the cycle efficiency, the back work ratio, and the net work output as the pressure ratio or RP is increased? We can investigate this effect by looking at the cycle on the TS diagram. As shown here, we have three different Brayton cycles. The first one is at RP of 2. The second one is at RP of 10. And the last one at RP of 16. All of them operate between the same maximum and the minimum temperature range. Now, let's have a look at the first one, RP equal to 2, or the cycle in red here. The shape of the first cycle is a narrow strip with a low pressure ratio. The next one in green is at RP equal to 10, which looks pretty much like a diamond shape. The last one in blue is at RP equal to 16, which looks like a vertical stripe. We have already known that the area enclosed by the cycle represents the network output. You can see that for these three cycles, the areas of them are different. We want to determine which pressure ratio will give us the maximum network output. So we have to write the network output as a function of pressure ratio. Now, the network output can be calculated by using the turbine work minus compressor work. The compressor work and the turbine work can be determined by doing the energy balances around the compressor and the turbine. We can then write the network output as a function of temperatures. We have to manipulate this equation to write the network output as a function of pressure ratio. First, we have to pull T3 out of the first bracket and T1 out of the second bracket. The term in the first bracket becomes 1 minus T4 over T3. And the term in the second bracket becomes T2 over T1 minus 1. From the isentropic relationship, we have the temperature ratio as a function of the pressure ratio. So we can change T4 over T3 and T2 over T1 in the bracket to be written in terms of pressure ratio to the power of K minus 1 over K as shown here. Now, we have written the network output as a function of pressure ratio. Note that T3 and T1 are fixed. Now, let's have a look at the conditions which we have zero network before we try to determine the condition which give the maximum network. The network will be 0 if RP equal to 1, which we don't have compression or expansion at all. The cycle will be just a single line on an isobar. We have point 1 and 2 at the same condition, and point 3 and 4 at the same location as well. The other condition in which we also have zero network is at RP equal to T3 over T1 to the power of K over K minus 1. At this condition, it means that we have compressed the air from point 1 to 2 at the maximum pressure and then expand immediately back to the lowest pressure. In this case, we don't have any heat addition or rejection from the process at all. The cycle is just a vertical line. We have no net work output. Work supply to the compressor is equal to the work done by the turbine. Now, Let's move on to the condition which we would get the maximum network output. For a fixed maximum and minimum temperature range of fixed T3 and T1, the pressure ratio that gives the maximum work is obtained from taking the derivative of net work with respect to the pressure ratio to be zero, and solve for the value of the pressure ratio. You can see that the equation that we obtained earlier is rather complex. So we'll simplify our function by taking Rp to the power of k minus 1 over k as x. The relationship that we developed previously becomes as shown here. Then we can take the derivative of W net with respect to x instead. It will be easier to determine analytically. The derivative result is shown here. When taking the derivative to 0 and solve for the value of x, we get x squared equal to T3 over T1. When we substitute x, which is Rp, to the power of k minus 1 over k back into the result, we get T3 over T1 equals to Rp to the power of 2 k minus 1 over k. We can then solve this final equation for Rp value. So the pressure ratio that can give the maximum network output would be T3 over T1 to the power of k over 2 k minus 1. This is the result that we are looking for. Now, for the ideal Brayton cycle, we have the following results as well, which are true. The first one, if Rp equals to Rp, that gives maximum network output. The turbine exhaust temperature will be equal to the compressor exit temperature, or T4 equal to T2. If the pressure ratio is less than the Rp max work, the turbine exhaust will be at a higher temperature than that at the compressor exit, or T4 will be greater than T2. On the other hand, the turbine exhaust will be at a lower temperature than that at the compressor exit, or T4 will be less than T2 if the pressure ratio is higher than Rp max work. For these three different cases, we can see that the shapes of the cycle will be different. Let's have a look at the first one, when Rp equals to Rp max work. The turbine exhaust temperature will be equal to the compressor exit temperature. The shape of the cycle looks like a diamond shape. Next, if the Rp is greater than Rp max work, the turbine exhaust temperature will be lower than the compressor exit temperature. The shape of the cycle looks like a vertical stripe. And lastly, if Rp is lower than the Rp max work, the turbine exhaust temperature will be greater than the compressor exit temperature. The shape of the cycle looks like a narrow strip as shown here. If we are looking for an opportunity to recover heat between the turbine exhaust gas and the compressed air, we'll find out that we can only have one possible scenario here, which is at Rp lower than Rp max work. It is impossible to achieve heat recovery from the turbine exhaust gas at the other conditions, since T4 is less than or equal to T2. At the given operating conditions, the pressure ratio which can give maximum network output is around 10. Increasing the pressure ratio further above Rp max work will start to decrease the network output. However, The Brayton cycle efficiency will continue to increase further, but at a lower rate with respect to the change in the pressure ratio. And that's all for this video. I hope you understand the effect of pressure ratio on the Brayton cycle performance now. Thank you for watching. Goodbye.